Alright, so we're going to be continuing to look at quadratic functions and their transformations.
Alright, so our parabola, our quadratic function, moves and acts kind of like our absolute value function. So whenever we are transforming our parabola across the coordinate plane, it has very similar transformations that we're used to already. So whenever we are looking at a, which is the coefficient here, it's right in front of the parenthesis, it's going to tell me which way my parabola is facing. Is it going up or is it going down? Now this is very similar to our absolute value function, if you recall. So remember that function looked like this. So they look almost identical, except for this guy has absolute value bars and this one has parentheses, right? So everything we already know still applies. So a here, if it's negative, it's going to be flipped over the x-axis. Alright, if a here is bigger than 1, which means it's anything bigger than 1. So if you see 2, 3, maybe 3 halves, 5 halves, anything bigger than 1, that means it's going to be stretched. So it's going to get skinnier and skinnier, and it's going to get stretched up. Now, if a here in the front is going to be between 0 and 1, then that means it's compression. So we are pushing it down. It's getting flatter and fatter. Alright, so a here tells us lots of different things about the shape of our parabola. So whether it's going to be flipped over the x-axis, and remember I hate that word flipped, it's reflect over the x-axis, or it's going to be stretched or compressed. Alright, so transformations of our parent function here. So remember, here's our parent function, f of x equals x squared. Now, moving around the coordinate plane, again, this acts just like our absolute value function. If we're inside of the parentheses here, and you happen to see a positive sign next to h, that means our graph is shifting to the left, alright, and h is actually negative. If you see a minus sign in there, that means h is positive, and we shift to the right. If we have k out here, if it's positive, that means we go up. And if it's negative, that means we go down. So again, same exact transformations we've seen before. We have our axis of symmetry here, which is always determined by the x coordinate of our vertex. So h, you see that? It's the guy right next to the x. And then our y coordinate of our vertex is our k that sits out here in our vertex form. Alright, so now I just want to describe the transformation that has happened from our parent function y equals x squared. So what do we do to y equals x squared to get to the current function that is shown here? Well, y equals x squared minus 5. That means k is 5, right? So my vertex is sitting at 0, negative 5. And what does negative 5 mean on the y coordinate there, my vertex? Well, that means I shifted down 5 units, right? So I shifted down 5 units. Part of my bad handwriting. Alright. Now what about number 2? Well, a couple things happening here, right? I have a negative sign in front. That negative sign tells me something, right? I'm reflected over the x-axis. But that's not it, right? So something else happened right here. That means that h is negative 1, right? My vertex is at negative 1, 0. Now, what does that mean? That means I went left 1, so I shifted left 1 unit. So 2 transformations there, right? 2 things happen. All right, number 3, where's my vertex sitting? Well, my vertex is at 1, positive 7. Which means that my guy here went to the right 1 and up 7. So he shifted right 1 unit. And he went up 7 units. So 2 transformations there also. Alright, so let's go ahead and graph this guy here. Easiest thing is going to be just shifting the parent function. So you can see that it was shifted up 3 from y equals x squared. So hopefully you recall our go-to parent function points, which are 0, 0, 1, 1, 2, 4. If you forget those guys, just go ahead and make a little T-chart, right? plug in values and figure it out. And then these guys get reflected over the AOS, right, which is x equals 0. Now all these points need to be shifted up 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3. And here's our new parabola. So let's go ahead and connect the dots. Right, our new points are 0, 3. Imagine that. If looking at this, you can see that h is 0, k is 3, so our vertex is 0, 3. This point here is 1, 4. This point here is 2, 7. Negative 2, 7. Notice how they have the same y coordinate. They should. Okay. Go ahead and label our axes here. Don't forget your sad old lonely AOS, which hasn't shifted from our parent function AOS. And that's it. Now, of course, there's other ways to graph this. You could first graph the vertex and then pick points around your vertex to find the other coordinates. But I think whenever it's in vertex form, which it is, y equals x squared plus 3, it's easiest just to do transformations. Alright, so what about this guy? Well, it looks like he was, let's see, shifted right 4. So our parent function here, my parent function points was shifted right 4. Moving my vertex to 4, 0, which is where it should be, right? Because h is 4, k is 0. Alright, now I want you to notice something, that our AOS has shifted, right? So my AOS is now here, it's in a different spot, because our AOS is always x equals h, and now h is 4. Connecting the dots here. Labeling our points like good children. Notice our y coordinates there the same. And there we go, fantastic graph. So again, of course, there's multiple ways you can graph a parabola. This is just one of them. Using transformations just one way. So if you're not comfortable with that, you can make a table. But again, transformations, I think, when you're in vertex form, is the easiest way. Alright, so this guy has lots of stuff going on. So let's just start with the fact that he was reflected, right? Reflected over x-axis. It was also shifted left 2, and then it's also shifted down 1. So I have multiple things that I need to do right now. So let's start with our parent function points, right? Okay, so our parent function points here need to be reflected over the x-axis, which, remember, that means you're treating the x-axis like it's a mirror. And so this guy here is 2 away, so it goes 2 away the other way. This one's 2 away, goes 2 away the other way. This one is 0 away, so it stays there. This one's 4 away, so it goes 4 away this way. 4 away this way. So let's go ahead and do that. Okay, but now this guy needs to be shifted left 2. So all the points need to go left 2, down 1. Okay, so I'm going to do that in one motion. Okay, I hope that's not too fast for anyone. But left 2, down 1, every single point. Notice how you can still see the symmetry there, right? You can still see how we have symmetry through our vertex. Now remember your vertex, your AOS is always the x corner of your vertex, which here is going to be -2. So our vertex here is -2, -1, which is exactly what it looks like it should be in my formula here. That's a good way to double check. The points we got here, let's see, that's -1, -3. This guy is going to be -3, -3. This guy, 1, 2, 3, 4, -4, -5. And this guy is going to be 0, -5. Go ahead and draw in our actual parabola. That guy's a little too pointy, right? It's supposed to be rounded, but you get the point, right? And vertex is right here. And then you, of course, label your graph. Everything's labeled. Perfect. And you move on. Alright, so this picture here shows that the path of a dolphin's jump is a parabola, right? So a quadratic function can model the path that a dolphin is going to jump out of the water and back into the water. So this is kind of like whenever I would give you a graph of a line and I'd say, write the equation of the line. So here I'm giving you the graph of a parabola and I want you to write the equation of the parabola. So there's a few key things I need. I need to know the vertex, which in this picture here is 3, 7. So the vertex is 3, 7. I also need an additional point that's on the graph, and that is going to be 9, 4. And we're going to be using the vertex form to help us solve this. So if you take a look at the vertex form, I have a y value that exists on my parabola, right? It's this guy right here. This y value, this x and this y, exists on my parabola. So that means this y and this y could possibly be the same if I need them to, alright? This x and this x I could substitute in, alright, because this x and y live on this parabola. Now I know h and k from this formula, right? H and k are from my vertex. So h and h, 3 goes here, right? 7 goes here. The only thing I don't know is my I value, but I know everything else. Now if I know everything else, that means that I can plug everything in solve for A. So that's exactly what I'm going to do. I'm going to plug everything in solve for A. So y here is 4. I don't know A. X here is 9. H is 3. K is 7. Alright, now I'm going to simplify. 9 minus 3 is 6 squared plus 7. Simplifying this again, I get 4. 4 equals 36A plus 7. Now this is a pretty simple problem that hopefully we can all solve, right? So I get -3 equals 36A. So dividing by 36, it's easy to see that A is going to be -1/12. So if I know the value of A, and I know the value of my vertex here, 3, 7, then that's enough information to go ahead and write the equation of my parabola in vertex form. So that's exactly what I'm going to do. A is -1/12. My vertex was 3, 7. So that means, using this formula, plugging everything in, I get y equals, A was -1/12. X minus, well, H was 3. K was 7. And that's it. Now double check. Notice how my A was negative? Well, think about the path of a dolphin, right? He's jumping out to the water and back in the water. A should be negative, right? Because we're opening down. Alright? So this is going to be the equation of the path of that dolphin jumping out of the water and back in the water.
Alright, now give these a try, describing the transformation from the parent function. Alright guys, please refer to the dolphin example in order to do this you try problem.